Hi, my name is Tomas. I do work for Enterprise DB. I'm a long-term Postgres contributor, developer, committer, and so on. And I'm here to talk about BRIN indexes, which is one of the types of features, one of the types of indexes available in Postgres. Right. First of all, I'd like to talk about why I'm actually doing this talk. I think BRIN indexes are really interesting, really useful in many cases, but are not very well known because it's introduced not from the beginning, and it's very special type of index. And I think also it's an interesting area for new developers. If you want to contribute to Postgres or something, you are usually looking for a part of the code that is sufficiently isolated from rest of the system, right? So for example, you are not going to work on the planner because that's about everything, right? It's a really complex thing. While indexes and BRIN indexes in particular are kind of isolated, right? So you can do stuff without breaking everything else. So if you are thinking about about starting to contribute to Postgres, this might be a good idea. And also, because it's a new thing in Postgres, relatively speaking, there is a lot of opportunities for improvements, right? And new ideas, completely different solutions. And I will try to present some of those ideas in this talk. By the way, if you have any questions during the talk, just shout or raise your hand right away. I will try to respond to any questions. So what I'm going to do during this talk is first I'm briefly going to explain what BRIN indexes are. Out of curiosity, is anyone actually using already BRIN indexes in the application, or did they create? Yeah, a couple people. I will briefly explain what BRIN indexes are. Then I will go into advantages and disadvantages of BRIN indexes, and we will look into some recent improvements that will hopefully illustrate what improvements are possible, right? What you can do in indexes, new stuff. And I will also present a couple ideas for improvements in the future. Some of them are already being worked on, so we can maybe do a review or test the idea on your application, or there are new ideas that haven't been developed at all. So it's completely new greenfield. So I promised I will briefly explain what BRIN indexes are, but I will do that by first explaining what BTREEs do, right? BTREE is the original classical index in most databases. It's a tree-like structure. And what is important to notice is that there is a one-to-one mapping between index entry and the rows in the original table, right? So if you are inserting a row, you will end up with one entry on the leaf page in the index, right? So there's one-to-one mapping. Those entries are organized in a tree, and those are great for searches for point queries, right? So if you are searching with the where condition for equality of a key, or maybe for a range queries or something, that's perfectly fine for a BTREE index. And they have many advanced options, capabilities, for example, you can do sorting using an index, right? Because indexes are, BTREE indexes are based on ordering, so you can just read the data from the index in a sorted way. And we can do covering indexes. If you do a unique constraint in Postgres, that is automatically backed by BTREE index, things like that. And they do support all possible execution strategies like index scans, index-only scans, bitmap index scans, and so on. But the main problem with BTREE indexes is that because they are one-to-one mapping, they can be quite large, right? So for example, you can have a terabyte table, and the index on the primary can be like 100 of gigabytes, right? So that's like a disadvantage. But you can imagine the index a bit like this, right? So you have like a root, which is a page, but usually the fan-out is much larger. I only show like binary tree essentially here, but it could be like 100 different values on each level. And then on the leaf page, which is over here, you have essentially a mapping from the key to, for each row containing the key, something we call CTID, which is essentially a physical location of the row, right? So you know that if you are searching for this key, you need to go to the table on this location. And that's the tuple that is matching the condition, right? Block indexes or BRIN indexes are like a completely different type of animal. They do not have the one-to-one mapping between rows and index entries. And instead, they chunk the table or split the table into smaller chunks, like 1 megabyte chunks by default. And they have some sort of summary for each of those ranges, right? So for example, you have the first one megabyte table, and you know that the minimum and maximum for the key is, you know the minimum and maximum for the key, right, in the range. So what you can do then is actually quickly eliminate large parts of the table that can't contain your key, right? So for example, if you know that the minimum and maximum is 1 and 10, and you are searching for a value 20, you know that it simply is not in that chunk of the table, right? There are other types of summaries. The minimum and maximum is easy to understand, but there are like for spatial data, like bounding boxes and regions and so on. That's what we call inclusion. When for BTREE indexes, I said that they support all types of index access methods, right? Index scan, index-only scan, and so on. BRIN indexes do not allow that because because you don't have the one-to-one mapping, you can't do a regular index scan. The only thing you can do is essentially a bitmap scan, which says like, this chunk of the table probably matches, and then you need to scan the chunk of the table which is not eliminated by the BRIN index, and essentially to read all the tuples there and check again the key. So that's kind of like a disadvantage, but also because it means it's not great for point queries, right? If you are searching for individual values, the BTREE will be much faster, right? Because it leads you directly to the exact tuple in the table. The good thing, however, is that this is really cache friendly because bitmap scans are essentially a sequential access, right? So it's like cache friendly and more suitable for when you actually are reading large amounts of data. And you can imagine this a bit like this. I try to visualize that. So you have a table, which is like a data file, which you split into 1 megabyte chunks. And that for each of the chunks, you store like the minimum and maximum for the key in that chunk, right? And I visualize that as in a 2D plane. This is like a position in the data file, and then you have the different values from the domain of the key, like intervals essentially, right? So when I'm searching for a value 250, I find all the ranges that might actually intersect with, might contain the value based on the minimum maximum. And I know that I only need to scan this 1 megabyte chunk of the table, right? And I can read all the tuples from there, check the condition again, and then output only the tuples that actually match the key. And a very simple example, you can imagine a table with a single column. I only set fill factor to kind of like simulate wider tuples, but that doesn't matter. Then I insert like, I think 10 million rows that simply are modulo 100,000. So it kind of like wraps, it goes up to 100,000, wraps back to 0, and so on. So it's like repeating. And then I create the index on the table using a BRIN access method, right? So essentially, this is the only thing you need to do when you want to create a different type of index in Postgres, right? If you omit that, it will be the default access method, which is BTREE. If you say using BRIN, we will create a different type of index. On a couple slides ahead, I will show you how to specify additional parameters, right? Because you can tune the index a bit, but that's for later. And then, right. So now what I do is I essentially do what the index does, right? I use the system column CTID, which is for each row, you can select the position, right? And that's like a block number and position on the page. And I split that into 1 megabyte chunks. And for each chunk, I calculate the minimum and maximum in that chunk, right? So this essentially says me like the first megabyte has values 1 and like 3,000. The second megabyte has values between these values and so on, right? So this is what the index is going to do. And another way to look at this is using an extension which is called page inspect, which is in the contrib modules of Postgres, and it allows you actually to inspect different data files, right? And I'm using a function which is called BRIN page items, which I look at the index I created in the example. And that's exactly the same thing, except that instead of calculated from the table, I actually look at the index directly, right? And it actually shows me exactly the same values here. Those are the minimum and maximum. This is a visualization of the index, right? This is what is stored in the index. And these are the block numbers, right? So each block is 8 kilobytes, so it's like 0, 1 megabyte, 2 megabytes, and so on. So this is essentially the same thing as before, yeah?
So just to clarify, that in the index pages, it stores the range of block numbers that index metadata describes.
Right. So essentially what the index does is like, it's the first block number, which is like 0, 128, and so on. And then a summary for that whole block range, right? So imagine that you actually read the data from the first megabyte and calculate minimum and maximum, and you store that minimum and maximum in the index.
So then there must be some way of going into the heap and saying, scan this range of blocks.
Well, I mean, yeah, you will read this from the index. You will find the matching rows, matching entries in the index. And then you will use this, which is the block number where the range starts in the table, right?
So that's included in the bitmap for the bitmap scan?
Well, you will then use this and say, like, I need to read the blocks between 0 and 127.
I didn't think a heap could be directly addressed by blocks.
Sure. I mean, like, that's the default how you read data from table. But the database does that automatically in the background, right? It just this is just translated into essentially position in the file.
Sure.
Right? So the database first reads the index, determines which chunks it needs to access, and then reads them from the data file of the table. So does it explain? I can maybe show you an example later. Like,
Yeah, I don't want to take up too much time.
yeah, okay. I mean, after the talk, for example. Right? Anyway, what are the main advantages of BRIN indexes is that the table is like it's a fairly small table, for example, right? So it's like 3.5 gigabytes. So it's like 500,000 8-kilobyte pages, roughly. But the BTREE index by default, if you create it, it's like 65 megabytes, right? So it's like a small table, reasonably large index. But the BRIN index only is like less than a megabyte. So it's like much, much smaller than the BTREE index, right? And then if I do a search using a particle value, what this will do, it will first, you need to read the execution plan from the, from the inside, right? We first access the index, we identify which ranges actually match the condition. We find that actually we decided to scan roughly 5% of the table. So we eliminated like 95% of the table at the very beginning. Then the bitmap heap scan actually scans all of this, and it finds only the 100 tuples that actually match. Right? So the idea of the BRIN index is actually to eliminate as many blocks in this step, right? So what are the problems of BRIN indexes? I mean, like, why are we not using them all the time? So first of all, it requires some sort of correlation between the data and position in the table. I mean, in the example, the data was perfectly monotonic most of the time, right? So the ranges were like not overlapping and not very wide. It was great. And it's, for example, it works perfectly fine for like timestamp cons. If you have a table that you append only, and you always use the current timestamp, that will be perfect for BRIN indexes, right? But as soon as you start like updating the table, that might move tuples from one position in the table to somewhere else, and so on. It will increase, like make the ranges larger. They will start overlapping, and it will be less efficient in eliminating parts of the table, right? And there are, of course, some data that is not correlated at all. Like, for example, UIDs. If you create the BRIN index on UIDs, that's going to suck, right? Because those are perfectly random, or more or less random. So the ranges will be very wide, impossible to eliminate, right? So what I mean by that is that if I take the same example as before, but I update like 1% of the table to be 0, and 1% of the table to be like the maximum value, right? Then, I mean, like, we will scan the whole table. We will scan the 100% of the ranges because we've been unable to eliminate anything, right? And that's just because we have updated like 1% of the table to make the ranges very wide, right? So then the ranges, the index actually looks like this, right? Essentially, each range, each 1 megabyte chunk has minimum and maximum, like the global minimum maximum. Right? So you can't actually eliminate anything. And if you visualize that the same way as before, it looks like this, right? So every time you do like a search, it will intersect with almost all the ranges in the table. And you will scan anything anyway. So it's like almost like a sequential scan, except that you are doing additional work. Right. Yeah. So, which leads me to the first improvement in Postgres 14. which is exactly about dealing with this sort of like imperfectly correlated data, and that's min-max-multi, which is like another operator class, which implements like slightly different summary, right? Instead of keeping just minimum and maximum, we keep multiple ranges, multiple intervals for each block range. So you can imagine that, which is great, exactly for tracking those outliers, right? So for example, for the first range, we will have like 0 to 3,000, and then the outlier 100,000. Instead of having like one huge, very long interval, we will have something like this, right? And that means that if we get a value search for here, for example, we know that it doesn't intersect actually with the summary, right? And we can still eliminate the range. So this is how you actually use a non-default operator class. So we say using BRIN, and then you specify the name of the operator class here, which is like for integer 8, which is big int, min-max-multi, operators, and then you see that actually we managed to eliminate even more, even making the index even more efficient than with the regular min-max operator class, right? So, which is great. It works perfectly fine for this type of almost correlated data with some outliers. The disadvantage, of course, is that the index is a bit larger, right? So for example, instead of 160 kilobytes, it might be, I don't know, half a megabyte, right? It's like a small multiple of the original index. It's still much smaller than the BTREE. So the other thing implemented in Postgres 14 is something we call Bloom. I mean, like, I assume that all engineers here ever heard about like Bloom filters, right? So the idea is that instead of keeping minimum maximum, you can keep any other sort of summary, right? For example, a Bloom filter. So instead of like calculating minimum maximum, you build a small Bloom filter for each of the ranges. The good thing is that this is perfectly suitable for, like much more suitable for random data, right? So for example, if you have IP addresses, chances are those are like very random, right? But you will only have certain number of distinct values in each range. And if you build a Bloom filter, you will be able to answer equality questions for that range. So you will say like, okay, does this range contain this IP address, for example, right? So here's an example which I use for UIDs. I mean, like, that's a type where you are very unlikely to do range queries, for example, right? So equality searches are the only thing you ever do with UIDs. So you can create a table, again, 10 million rows, 100,000 distinct values. You will specify a different operator class, just like we specified the min-max-multi on the previous slide. And then you can do searches like this, right? So you can search for individual UIDs, and you will get this. Of course, a BTREE index is going to be much faster here, right? So this took like a second on my laptop or whatever. It might take a couple milliseconds using a BTREE because it still needs to do a bit of random I/O, but it will go directly to the individual tuple. This illustrates the thing that BRIN indexes are like a trade-off between index size and speed, right? They are much smaller than BTREE indexes, but they are much faster than a sequential scan, right? To give you the speed up. And you can even tune the Bloom filter a bit, because the Postgres doesn't have any like good way to determine how many distinct values to expect in the ranges and what is the false positive rate for the Bloom filter and so on. So you can specify that like this. This is another feature, I think, in Postgres 14, which is like operator class parameters for all indexes. And the index is like much larger than the min-max, of course, much smaller than the BTREE, and still improves the performance of it. I think the Bloom filters, Bloom BRIN indexes are more an illustration that you can actually implement very different types of summaries. So if you have a good idea for like, if only I could implement this type of summary for my type of application, like, I don't know, it could be something for machine learning or whatever, you can specify, you can build a very different type of summary using the infrastructure. So those were the improvements in Postgres 14. What is the future of BRIN indexes? So we already have a couple patches that, however, need a lot of testing feedback. So if you are interested in this, I would love to hear feedback from if you try that on your application or something. So first thing is that I mentioned that BTREE indexes allow actually sorting, like sorted output. And we can actually do something similar for BTREE, so for BRIN indexes in some cases, right? Because we can kind of like incrementally sort the data based on the min-max ranges. Because if you only need to input the first 100 rows, for example, you can kind of like look at the first couple ranges in the BRIN index and only sort those, right? That's the kind of the idea of the BRIN sort, which is the first section. Then we have a patch that improves a special, like this type of queries, right? Where you have like where condition and the key is in an array or a list of values, which now works, but we essentially do a separate index search for each key, right? Instead of scanning the index once, we do that once for each key and then merge them together, which is really inefficient. Then when you are creating the index, currently it's like there is no parallelism for BRIN indexes. We do support create index parallelism for BTREE indexes, but not for BRIN. And we have a patch that actually fixes this. One feature, one improvement that I didn't mention before is hot updates. Who knows what hot updates are in Postgres? Right. So for the rest of you, when you are updating a row in Postgres, and there are indexes on the row, on the columns that you are modifying, then you need to update all the indexes, right? Even if there is just a single index on the modified columns, you still need to update all indexes. The improvement here is that if you are only updating updating columns that have BRIN indexes on them, then you actually don't need to do this. You just need to update the summary indexes, right? Which is like a significant speed up because index bloat is a major issue in Postgres. And if you are not creating additional index entries, that's like improvement. And that's also, yeah?
So on that last point, if you have multiple columns with BRIN indexes on them, I guess maybe that's not meaningful, but when you update one column, do you need to update both indexes?
Yes. So originally, so the question is like if you have like multiple BRIN indexes on different columns, I think we need to update all the summary indexes, yes. And originally there were like two levels, right? So either you updated all indexes or no indexes. Now we have like three. We can do like no indexes, only summary indexes, which is like BRIN, or all indexes, right? So yeah. And what are the crazier improvements that might actually happen? So one problem with indexes in Postgres is that we don't do toast for indexed data, right? So, and for BTREE, that means that you only can insert like 1/3 of the page in the index. So if you have like, for example, a text value which is longer than 1/3 of 8 kilobytes, that will fail. You can still do compression, of course, but if it grows beyond this point, it's you will be unable to insert the table, insert the value. For BRIN, it's kind of worse, right? Because instead of keeping individual values, we are, for example, keeping two. We are keeping minimum and maximum, right, for each index entry. So you can kind of like hit the issue sooner. And it's also a bit unpredictable, right? Because you will try to insert the tuple, it will fail. You will try to insert it again, it will get routed to a different part of the table, and it will succeed, right? Because it happens to combine with a different like summary, and will be fine. So it's kind of like unpredictable, and it would be good to fix this, right? Improve the user experience, because right now it's like, what do you do? I mean, like the only thing the user can do is kind of like retry, retry, retry. And we don't even know if it's like a persistent issue. If every time they do that will result in a failure, or if it's something that can be, resolved quite quickly. So I think that will need to be solved. I mean, like, luckily, people generally don't create BRIN indexes on large columns, so that's not very common. But for example, the Bloom filters, Bloom indexes are much worse, right? Because it's not about the individual values, but you are kind of like building a random bitmap over time. So at some point, it becomes like non-compressible and fairly large, right? So that's a problem. The other idea, and I'm not sure how feasible that is actually using BRIN for routing the tuples into parts of the table, right? So for example, if you have a timestamp column and you have a BRIN index on that, you probably do want to kind of keep the data more or less correlated to that, right? So maybe if you insert a new or do an update, the new version should be kind of like selected, the position should be selected not just based on like free space on the page, but also like looking for a part of the table where the value, the timestamp in the BRIN index would kind of like fit nicely, right? I'm not sure how feasible that is or how expensive that would be, but at this point, we are not maintaining any correlation at all. It's like complete, like pretty much guaranteed to degrade over time. And there's of course a lot of like open questions, like what do you do if you have like multiple BRIN indexes that should be respected like this, right? And then there are like more open questions. First is like implementing different types of summaries, right? So for example, instead of keeping just min-max and Bloom filters, maybe you could have like different types of summaries like prefix sets, right? So if you have strings and you have a lot of like prefix searches, maybe you could use like a different type of summary to speed up those queries, right? To eliminate those a lot of keys, right? Or maybe you could use BRIN to speed up count queries, right? So instead of keeping just like filtering in each range information, maybe you could also have additional metadata that could be useful for answering questions like select count star or something like that, right? I'm sure there's like a lot of problems with that, but we only do, for example, index-only scans for all visible pages anyway. So maybe you could do something like that for BRIN indexes too. And the last thing is that while working on BRIN, and BRIN was introduced in Postgres 9.5 in like 2016, I think, I ran into a bunch of bugs, like long-standing bugs that have been there since the very beginning. And I realized that actually we do have a lot of tests in the Postgres code base, but those are regression tests. Those are fairly well predefined sets of tests with very low concurrency, because we essentially just run like a single SQL script. And it's not like a massive number of updates from different sessions and so on. And also all the steps are executed in very strictly predefined ordering, right? So there's very little variability in the tests. And all the bugs that I discovered were about like highly concurrent environments and so on. So I've been working on like randomized stress testing, which essentially means that we do a lot of different operations in like a random stochastic manner, and then we do a check between results produced from a sequential scan, for example, and an index, right? So it's like, does the index actually produce the correct result with respect to sequential scan? And I think we need to improve and continue working on that. For BRIN, it was kind of like very helpful because it's not a very widely used feature, so the amount of testing from production systems is limited. And I think it would be good to have, more ideas, more variability in the stress testing. Right? So at this point, I'm not aware of any outstanding bugs, but if you want to, help with something and you don't feel like coding in C, doing something like a stress test, and with your strange workloads or something you can invent would be very helpful, right? It's a way to improve the quality of the product by means of testing. And that was all for me. If you have any questions, I'm happy to answer them. Yeah. So as I mentioned earlier, this was partially meant as an idea to help new developers to do the first thing in Postgres, contribute new patches or do a review or something. So if you want to talk about that, even if it doesn't actually mean working on BRIN, you want to work on something else, I'm happy to help with that. Right? So that's all from me. Yeah?
So this isn't specifically BRIN, but are your stress tests in the repo? Is there a way to run them? And
no, I mean like, so I think that would be, so the question is, if the stress tests are in like a repo or something, they are on my laptop because it's a very ugly bash script with like something very primitive. One of the reasons why we don't have them in the official code base is that we want to run the regression tests very often on a large number of machines. But I think making that more like usable and you know, kind of like moving something like that into the code base would be exactly one of the possible improvements for Postgres, right? Yeah, something like that, right? So I'm okay with like sharing the scripts or whatever, but as I'm warning you, it's like kind of like ugly. It did the trick for me, but we need to kind of like find a better way to actually implement stress tests in general, not just for BRIN, but for many other parts of the code base. Does it answer the question? Yeah. Yeah, okay. Yeah.
Oftentimes when I have time series data, I think about BRIN, but usually it's like an ID plus a timestamp, and I want to index on both of them. If I could partition on the ID, say I don't have very many IDs, and I could create a partition for every ID, then do you think, it seems like BRIN would be a really suitable index for those partition tables?
So, yeah. So you can't have an index that is both a BTREE for one column and a BRIN for another column, right? It's either BRIN or BTREE. But if you partition the table by the ID and then create the a BRIN index on that, that would work. The other thing you could do is you could use something like BTREE gist or BTREE. Well, no, that doesn't work. But you could create a multi-column BRIN index with the timestamp and also with min-max, for example, on the IDs, or maybe bloom on the IDs. And then that would be useful actually to work together. Right?
Okay, even without partitioning.
Yeah, even without partitioning. I mean, one advantage of BRIN indexes is that you can combine the bitmaps very easily, right? So you can build one bitmap using one index and another bitmap using another index, and then you combine that together for essentially evaluate both conditions at the same time. Right? So that would work. You can try, of course, the partitioning. I don't know how many partitions, for example, you would need, but you have to try. Yeah. Okay. Yeah.
What is your recommendation for if we have multiple aggregate queries with the same filter condition?
So I'm not sure what exactly you mean.
Aggregate query, like some.
Yeah. So I don't think that's really related to BRIN, but
It's not a BRIN, that's like
yeah. So if you only want, so if you only need the aggregate fold, the filtered data, then I would just use that as a where condition. I'm not sure why you are using filtered aggregates.
No, I just wanted to know if it's like a BRIN. I know it's not just not to confirm.
So the filtered aggregates will not use BRIN at all. Of course, we only use BRIN for like the where conditions and so on. So if you instead of filtered aggregates, you use a where condition and regular aggregates on that will use BRIN, of course.
Yeah, because in the example you mentioned count star with where condition.
Yeah, but that's like a wild idea maybe for the future, right? I mean, like I don't know how to implement that, right? So there was more like maybe we could do that. I don't know. Okay. Yeah, that's all for me.